This is Mark McKeon at Titus Performance. We're here again today to have another video about Cleveland blocks, and as promised, this video is going to be about deck heights and sleeve lengths. First off, let's just give you a little quick review of what makes the Cleveland, or the Titus, the innovator in the Cleveland world. Just to go over a few of our features from the start. We have solid lifter banks so that we can move lifters around. We can put Windsor angles in this, we can put Cleveland angles in this, or if you engine builders and engine designers want to design your own lifter angles, we can do those as well. We do make this block in a deck height anywhere from 9,100 to 9,700. As we said in our last video, our cylinder bank is much wider, which gives us the ability to put a bigger barrel around the cylinder, support the cylinder, and give this cylinders a lot of support. You can see the additional where we've moved these holes out just a little bit to get this much material outside of the sleeve. So we've got about 350 thou outside of the sleeves in the aluminum. We added the bosses here for you power adder guys that run multiple bolt patterns. We've got the additional, we can either run 14 head bolts, which is standard Cleveland is 10. We can either run 14 or 18 head bolts, depending upon how serious you want to go. We do offer the block in a solid water version or a non-water version for the guys who are running the big cubic inch stuff with alcohol, and you really don't need water in the block, and you want that extra rigidity in the block. We offer that. The block does come with 4 bolt main caps. These are billet main caps. The center 3 are splayed. We actually widen the main cap out to the outsides of the pan rail so where we can still get a pan on the block. But we did relocate the bolt holes in such a fashion that we added structural integrity inside of the block that actually distributes the bottom of the load, that distributes the crankshaft load across the bottom of the block instead of being point loaded here on the main cap fasteners. We did also add a pad down here at the bottom for the guys who run stick shift cars, such as myself. And what that's for is that we can mount our starter here to the block so that we can remove the transmission, the bell housing, and we don't have to take the starter out of the car to do so. So it makes between round servicing of your clutch a whole lot easier when you don't have to remove a whole lot of parts off the engine. We do use a screw-in freeze plug, and that pretty much is the big things that you can see as far as the features of the Titus. But back to our original purpose of this video. The purpose of this video is deck height and why we gave you the choice. And the sleeve length, really what you're looking for when you are, and what you need as far as a sleeve. Now, when I say what you need, that's still up to you. We do give you the choice to design the engine pretty much however you want, because we have enough latitude in our casting in order to do so. This is a 9.5 deck casting. This is pretty much our middle of the road casting. In our range from 9.1 to 9.7, this has become very, very popular. This block has right at a 6-inch sleeve in it, as opposed to this 9.2 deck. Now this is a block that was cast about 10 years ago. This was one of the Todd Buttermore blocks. This one has a 4.155 bore. It is a 9.2 deck and has a 4.5-inch sleeve in it. So what we're going to do is just show you a little bit of the differences of the blocks, the difference of the sleeve lengths, why we do things the way we do, and if you so desire, you can build these things however you want. Well, first off, this is a again a 9.5 deck with a 6-inch long sleeve in it, and we don't leave the sleeve hanging way out of the bottom of the bore, trying to make this block something that it's not. We're not trying to take a 9.2 deck block and make it a 9.5 deck block and make it something that it's not. The reason we built our castings the way we did was to give you the choice to be able to do things properly, to build a big cubic inch engine properly, and without having to go through some of the steps that I'll explain to you why, as you don't want sleeves hanging out of the bottom of your block. First off, we can just do some of the quick math on this. Is if you have a block with a sleeve in it that's right around 6 inches long. Draw a sleeve. This is 6 inches. And this, a popular combination for this 9.5-inch deck block has been a 4 1/4-inch stroke crankshaft. There's still plenty of room to get a lot of stroke in here. There's plenty of room to get a long connecting rod in it and still have a piston that has enough height on the piston to be able to give good support and also give good piston longevity should you want to drive it on the street, racetrack, or however you want to ride this thing. But back to our math. A 4 1/4-inch stroke on a 6-inch sleeve is, I want to show you that it's actually a pretty good design. I'm having a hard time drawing a straight line here. But if we do a 4 1/4-inch stroke, and we take a piston, such as this guy up here, which this is one of our street style pistons that we run in our crate engines, and it's been a popular piston design for, we use the same kind of design for bracket racing and things like that. That piston is about 1/900 in total height from the crown of the piston to the bottom of the skirt. So if we take that 1/900 and add that to our 4 1/4, what we're going to end up with is, at bottom of stroke, you end up with about 150 thousandths of the piston skirt actually that might hang out of the bottom of the board. And 150 thousandths, that's roughly 1/8 of an inch, is not very much when you look at what we're actually doing with that kind of stroke. Pistons now are designed to where we don't really use the bottom of the skirt to support the bottom of the to support the piston anyhow. The point of the piston where it actually pushes on the cylinder is much higher. It's up here right next to the blow ring. This does stabilize the bottom of the piston, but what we're not doing is using the very bottom to stabilize it, so that if it does poke out through the bottom of the bore about 1/8 of an inch, you're not losing any stability. You can also see that if the bottom of the piston were to hang out the bottom of the bottom of the bore, that you still have plenty of room, that the pin is up inside of the bore, and the piston actually pushes on the bore about where I'm drawing this black dot on the piston. That's really the sweet spot on the skirt. Now, to go to an extreme case, this is a piston out of a 500-inch engine. And you can see actually the wear mark. This is the wear mark. I'm going to actually draw a circle right around it. That's the wear mark on, that's where the piston actually pushes on the cylinder board. So you can see that when this piston, even though this engine has a 4 1/2-inch stroke, and we use a sleeve that's longer than 6 inches, there's about 100 thou that actually sticks out of the bottom of the board. You can actually see the witness mark of that, where it actually comes out of the bottom of the bore, right here where I'm drawing the Sharpie. So even with a 4 1/2-inch stroke, our 9/7 deck block with a long sleeve in it, the piston still stays in the bore for the most part, even at bottom dead center. As a matter of fact, this particular piece, 500 inches, we tested one of our engines that we built just to see how hard we could push on the cylinder bores on blocks. We tested, what we did is we built a 9.3 deck engine. We put a very short connecting rod in it. We put a long stroke crank in it, which was a 4/100 crank, and a very short piston in it. And the piston hung out of the bottom of the bore. The bottom of the piston almost hung halfway out of the bottom of the bore. The wrist pin, the bottom of the wrist pin on the piston was about even with the bottoms of the cylinders. And what our purpose was to do was to try to push on the cylinders, to side load the cylinder on the power stroke, and really see what we could do on the side of the block and how we could distort the cylinders, and also what it did top to bottom. And the results that I found, I'm pretty happy with after 3 years of running, and I've run that engine hard, and I mean, when I mean hard, I mean 9,500 and 9,600 RPM burnouts, 9,700 RPMs on the shifts. The pistons came back. The pistons weren't damaged. They had a little bit of scuffing on the bottom, but any engine that runs at 9,700 RPM has a little bit of scuffing on it, because naturally we run the pistons loose in the bore on an engine like that. But the good part about it is when I bore gauged the block, we didn't hone the block or anything, but when I bore gauged it, the most at a round that we saw on that block that had been beat on for 3 years, plus some Engine Masters competition time, was about 1.5 thou. And 1.5 thou, it may sound like it was distorted, but there's a lot of blocks that don't come with a fresh bore that are within 1.5 thou to begin with. So I was very happy that that block stayed straight, it stayed round, even though we punished it as hard as we could in order to test it. We felt it was better for us to test our product than someone else. But back to blocks with proper sleeve lengths. I'm happy to say that, you know, there's an old expression that if you build it, they will come. I'm happy to say now that they are coming, and they're coming very fast. We've had some nationally renowned engine builders actually ordering bunches of these blocks in 9.7 deck heights. I really didn't think 9.7 was going to be the seller that it is, but in the last 3 months we've sold more 9.7 blocks than we have any other deck height block. It seems that the guys are real big into building the big cubic inch stuff like we are. Given the architecture, they're finally learning that engine builders are finally learning that the Cleveland architecture will take the big strokes. So therefore, it was very important for us to design the cylinders and everything in order to be able to handle those big strokes. There's even an engine going together right now that the block was just sent out that is bigger than my 500 cubic inch. I believe the customer said he wanted to be the biggest thus far, so his will be bigger than my 500 inch engine. It has a bigger stroke than my 4.5 inch. I'm not going to disclose all that. I'll let him do that when it comes on display, and that engine will be on display this year in Indianapolis at the PRI. But back to a couple reasons why you don't want blocks with sleeves hanging out of the bottom of the bores. When you put a sleeve in the block, and you have, which is what a dry sleeve is. A dry sleeve is supposedly a sleeve that is supported all around. These are not wet sleeves, they're not diesel blocks. And we don't do the kind of things that a mod block does where we gut the whole block out and put a sleeve in it. These sleeves are supported. And again, we built the Titus to where it has the most support around these sleeves, and we had to modify the exterior part of the block in order to do that. But when you put a sleeve in a block and it hangs out of the bottom, if you're an experienced machine shop guy who's honed blocks, you'll attest to this. When you go to hone a block that has a sleeve that hangs out of the bottom and is unsupported, it's really hard to get a straight round cylinder. Not to mention, when you take a block that has a 4.300 OD sleeve and you bore it out to 4.200, that only leaves you 50 thou of the sleeve. Now that sounds thin, but I know of some mountain motor 800 plus cubic inch guys that run their stuff down to 32. So we still stay in the safe range even with our sleeve there, so that we don't get any pinching of the sleeve when the piston starts to push on it. But what happens is, when you take a cylinder and you run a hone down through it, and we'll take the piston out of here and we'll put it in the honing machine real quick. And my pen is running out of ink. When the hone goes through in the bottom of the cylinder, the hone is actually pushing out on the sides of the block. And what happens is, if your block is here and here, and you have this unsupported part of the sleeve, what happens is the hone actually will push on this part of the sleeve, and it'll blow the sleeve out. So the sleeve expands when the hone is pushing on it. When the hone goes back up the cylinder, the sleeve just pushes right back in. So what happens is, you don't really get the proper cutting action on the sleeve. So the sleeve begins to be tight. So in an enlarged fashion, what you get is you get a sleeve that comes down and gets tight at the bottom. Now, another thing that you really don't want with your sleeve hanging out of the bottom is when the sleeve actually comes down and gets so close to the center of the main bore, you have webs in the block. Well, if your sleeve is so much longer that it comes down and your hone is blocked by the main, you can't overstroke the bottom of the cylinder in your hone. And we all know, guys that hone blocks, is you have to overstroke the bottom of the cylinder the same down here as you do up here in order to get a straight round cylinder. Otherwise, you're going to work yourself to death trying to hone a block and get it straight, and it's still not going to get straight because you're going to have to modify a special set of shoes in your hone in order just to hone this little part down here and keep it open. So, not a good idea to put sleeves in your block that are going to be hard to hone. They're not going to support anything because they're going to be too thin. And the other part of that is, if you do the measurements, if you measure from the center of the crank to the bottom of that sleeve, which hangs out about 5/8 of an inch, you're going to find that the counterweights are going to whack it anyhow. So realistically, what you're going to do is you're going to spend a lot of time with a die grinder, let's say stroker clearancing your block, but you're really not even stroker clearancing it. You're just cutting something out that shouldn't have been there in the first place. Okay, what I have here is a model. This has been behind me the whole time. This is just a simple model of a cross section of a block with a piston and sleeves and crankshaft. And what it's modeled, this is a 9-2 deck block, so it's 9-2 from top of deck to center line. It is a 4-inch stroke, so from center of crank pin to the center of the crank is 2. And I have our piston that we looked at earlier drawn in. The piston is in white. The sleeves that we put in a Titus block are in green. Those are 5 and 5/8 of an inch long from the top of the deck. And this red sleeve here is one that is 6 1/8. And if we zoom in, you can see that a standard H-beam style connecting rod will hit the bottom of the long sleeve that sticks out of the bottom of the block. You can see that it'll hit, which is the point, I guess, to put it in so that you can grind it back out. So the sleeve is not only going to be sticking out and make the block hard to hone because you can't overstroke the hone, but it will also be cut on the bottom and be sort of knife edged and give you even less support yet, which then makes the sleeve prone to cracking. So if we look over to another position of the crankshaft, which we've put the crankshaft at bottom dead center, and look at the same two sleeves in the 9-2 deck block, you can see the piston on a 5 5/8 inch long sleeve in green. You can see the bottom of the piston hangs out about 185 to 190 thousandths. And that is not objectionable at all, because as we discussed earlier, the part of the piston that actually has the pressure point on it is right about where the cursor is. It's just above the midpoint of the pin and below the oil ring. So the piston is actually putting its pressure point on this part of the sleeve, which is still well up into the bottom of the sleeve. So even though the bottom of the piston hangs out just a very little bit, the pressure point is still well within the point of the sleeve. So you can see this extra part of the sleeve, even on a 4-inch stroke with a standard piston, 6-inch rod, it's too long and not even needed. So you'll find what you would need to do would be to more than likely cut this sleeve off, or you'd have to modify the bottom of the block in order to overstroke your hone, which would really do what us as aftermarket block manufacturers don't want to do, which is take away material in the main web. So it's kind of a catch-22. You're either going to grind away the sleeve so that you can overstroke it, or you're going to grind away part of the block, which is the structural integrity of the block. We do a lot of modeling to figure out what we're doing before we actually do it. This is a model actually of our Titus block. This is a complete CAD model that we use to design the block and design the tooling. This particular model is the actual model of the block that was used to make the tooling at the foundry. And while some folks think it's a big deal to cut up blocks, we actually prefer to design them correctly with 3D models beforehand so that we can actually see what we're doing. And you can see as a cutaway of this block, you can see the thickness of the sleeve material. So in an iron block, you would get this full thickness. In an aluminum block, you would have this particular thickness minus the thickness of the steel sleeve that goes inside of it. This thickness across here is right around 200 thousandths. So you can see there's about 500 thousandths outside of or thickness in a cylinder sleeve before we start machining on it. Other things that you can see here is you can see that where we did widen the block and we bulged the block out, as in our first video, there's still plenty of room for water passage around the cylinder sleeves. So as engines get bigger, they make more power makes heat. You have to get rid of that heat. So not only did we make the block capable of making power, but we also made it capable of running power and getting rid of the heat. So when these are used in endurance applications like road race, super late model, things like that, we have enough structural integrity to handle the power, but we also have enough water in the block to get rid of the heat. So there is more water in this block around the cylinders, around the outsides, than what there was in an OEM block. Another thing you can see here is the actual deck thickness of one of our blocks. We use a very, very thick deck, which gives us a lot of structural integrity around our head bolts. What you don't see in this particular model, in this particular cutaway, is we have added some structural features inside of the water jacket that actually support these bosses for the head bolts, so that we get a lot more clamping force on the head, and we also get a lot of rigidity in the block so that you don't actually warp the block when you torque the head bolts on it. We'll finish up today just by going over the few things that we did discuss and just making sure we've hit all the points. First off, what we're really looking to do is use the right part for the right job. If you want to build an engine on a 9.2 deck block like this guy, use a sleeve that's the appropriate length so that you can machine the block, you can hone the block, you don't have to remove material in the bottom of the block. Your piston will still be well supported. It's a properly designed engine. We have, and other engine builders have been doing it for years. What you don't want to do is try to take and make a 9.5 deck block, which has a sleeve that's over 6 inches long in it. What you're really not wanting is to try to make a 9.2 deck into a 9.5 deck block, because it's really impossible. No matter how long the sleeve you put in it, you're going to end up cutting it back. And then to figure out how to machine the block, if you're trying to leave the sleeve in there, you're going to have to clearance the bottom of your main webs. And the purpose of this whole exercise back in the day was to put as much material in the main webs. This is a prime example here on the Buttermore. You can see that it did not have solid main webs. That was one of the things that many racers and street guys alike asked for it to be updated, and it was, but it still is a 9.2 deck block. In closing, we just have to ask ourselves some common sense questions when it comes to the sleeve length and the deck height of the block. If you're told that your sleeve should hang out of the bottom of the block in an aluminum block, because in an iron block it does not have sleeves in it, if you're told that your sleeves are hanging out of the bottom of the block and that's what you need to build a stroker engine, ask yourself this question. Are you being told that only the aluminum block is good for a stroker engine? Are you being told that the iron block is no good for a stroker engine because it doesn't have sleeves hanging out of the bottom of the block? Sounds like there's a little bit of a contradictory story there. Anyhow, guys, I hope you enjoyed this video. Come back next time, watch our next video. We're going to talk about the oiling system on a Cleveland. We're going to talk about the priority main oiling system on a Cleveland compared to the OEM oiling system, or the priority main on the Titus compared to the non-priority main oiling that was standard on the Cleveland. Tell you a little bit about what we've learned over the years on these, making the OEM Cleveland block live, and also what we did to the Titus design to change all that so that you don't need to do some of that additional work. Have a great day, guys. See you next time.